Hello, ladies and gentlemen. My name is Simon Tipley from the International Food Safety and Quality Network. Welcome to Food Safety Fridays, edition number 105. Today we've got Robert Rogers from Metal of Toledo with us, and we're going to be discussing detecting. Oh, damn, I'm not even going to say it. It's about detecting contaminants in food products. It's a bit of a tongue twister. Right, it's good to have you along. Tracy, Enrique, Mastena, Tim, say hello in the sidebar. Tell us where you're from. Yeah, those of you who haven't been before, it's very easy. Just type your comments in the sidebar, click send. Save your questions till the end. It makes it easier. Just to say, the Food Safety Fridays program is sponsored by Metal of Toledo, Safe Food 360, Trace Analytics, AIB International, and DMV GL Business Assurance. I think my mind's going. I'm glad it's Friday. Yeah, these kind of organisations help to bring these programs to you, get you some bite-sized education and also a free certificate of attendance. Yeah, it's being recorded today. So afterwards, we'll follow up with to all registrants with the recording, the slide deck, and the certificate. So don't worry about that. So, okay, without further ado, I'd like to introduce you to Robert Rogers. See there, Robert?
Hello, hey Simon, Robert. How you doing? How you doing?
I'm great. You?
Great. Good to see you.
And you're in sunny?
I'm in, well, it's not so sunny Florida. We're getting a little bit of rain this afternoon, I think. So, but I can't complain.
You look like you're in a tropical rainforest. Right, okay, Robert, if you want to get your slides ready, I'll just tell the audience about next week. Yeah, next week, if you have a look in the sidebar, you will see a picture of George Howlett from Safe Food 360. And the Friday's webinar next week is Measuring, Monitoring and Oversight of Food Safety Compliance, How to Build a Compliance Model for Your FSM, Food Safety Management. So that's with George Howlett, same time next week. If you click the Register Now button, it'll open a new window and you can enter your details there and you'll be registered for that. If you want to get your slide, can you get your slides up, Robert? And then I think we're ready to go. Hello, Kathy from Seward, Alaska. Sabina, Springfield, Missouri. Who else? We've got sunny Jamaica. Patricia, good morning. Well, the sun's gone from Manchester, England, unfortunately. We're in the dark zone now. Anyway, here we are, determining detectability of detectable products. Say that a few times when you've had a drink. All right, Robert, over to you.
Thanks, Simon. Yeah, I figured I'd give you a little bit of a tricky title there for your Food Safety Friday today, Determining Detectability of Detectable Products. Of course, product recalls due to foreign material continue to happen. Common materials obviously include metal, glass, but we're seeing an increase of product recalls due to more difficult to detect materials such as plastic. Inspection technologies like metal detectors and X-ray inspection systems certainly are capable of detecting some of these contaminations. However, it's important to understand the true level of the detection. Depending on the material type, the inspection device that's utilized, detection may be a little easier to achieve, or it may be a little bit more challenging to achieve. Hopefully in this presentation, we're going to outline some general capabilities for both metal detection and X-ray inspection systems. We'll also explore what some material manufacturers are doing to make some undetectable materials now more detectable. We look at food contamination and the entire value chain of where products come from and how they're produced and manufactured. If you look through the entire value chain, really contamination can occur at any point. The example, even at the start of the process during harvesting, physical contamination could be as simple as a small stone remaining hidden among some raw vegetables. If not detected, they could be delivered with the ingredient to the processor, manufacturer, and eventually make it to the consumer. There are also varied and multiple entry points throughout that entire supply chain and processing environment where contamination could actually be introduced. The example shown here is a simple meat type processing where the most common weak areas would be on the receipt of raw materials or during the bulk product receipt, where you could have items such as injection needles that were broken off during inoculation, ear tags from the animal itself. Of course, then you move on into further processing where you have maybe a grinding stage or a cutting stage where the material is being broken down into smaller bits, where you have risks of the machinery breaking itself, you have risks of knife blades breaking off and things of that nature causing contamination risks. Finally, you have through the packaging stage, a lot of meat products in this particular case are ground meat would be packaged in what they call a meat chub, which is a sleeve of product that has metal clips on either end to secure the package closed. Sometimes those metal clips actually end up in the packaging itself and then, of course, gets sent off into the retail marketplace and gets identified or located by a consumer and could then result in, obviously, brand damage, potential recalls, things of that nature. So installing inspection systems.
Robert,
yes?
Sorry. Are you still on the first slide or have you moved on?
Right now you should see a slide that says different types of physical contamination.
No.
Next slide.
Yes, do it. You got it now.
Okay. Well, it seems like it's working now. Sorry about that.
No problem.
So now you can see the value chain that I was speaking of. I won't go back and spend too much time on this, but basically the point is that at any point in the process, whether it's the receipt of the raw materials through further processing, even on into the packaging stage, there are risks for contamination to be introduced at any point. And some of that contamination risk could be from the actual manufacturing equipment itself, product contact surfaces, points in the process where we're doing grinding and blending and these sort of things. So certainly installing inspection systems to help identify and remove that contamination, hopefully early on in the process as we can, that helps to identify when we've kind of got a loss of control that has occurred and can identify where we may have an increased risk of potential damage to, again, the brand, costly recalls, things of that nature. Look at kind of the quick agenda here. Today we're going to look at the two most common, I guess, what we would consider electronic type detection systems, metal detection and X-ray inspection. We'll look at basics on how those inspection systems work, just to give you an idea of what some of the detection considerations and limitations will be. We'll look at what some manufacturers are doing to certain products to make them more detectable, and then hopefully have some time for some question and answers when we conclude. We are cycling through the screens, correct, Simon? I just want to do a check.
Yes, we are, Robert.
Perfect. All right. So there are certainly many ways to control foreign material, and I look at controlling foreign material from really a holistic perspective, where even though Mettler-Toledo doesn't have anything to do with some of these items, I believe that they are a very important point in the process to help control foreign material, and that would be magnets or screens or filters or sieving the product. Those I would consider what I would call physical ways to control foreign material. Obviously, the magnet is going to trap the material physically. The screen is going to trap the material physically. When you look at what I would consider electronic foreign material controls, like metal detectors and X-ray inspection systems, that way we're really basing detection upon an electronic device to notify us when there's a potential problem with that particular product. I believe that really the combination of all of those prevention measures are important when trying to protect a product against foreign material. And certainly depending on where we are located throughout the value chain and throughout the process itself, one solution may be more successful than another solution, depending on the location, the product conditions, many factors. We'll go over some of those as they pertain to metal detectors and X-ray inspection systems. We look at metal detectors. Basically, we look at those as conductivity detectors, meaning anything of a conductive nature traveling through the detector will have an effect on the output. So product conditions can have conductive natures. Products that have high moisture content, products that have high salt content, products that are running at very high and warm temperatures can have an increased conductive nature to them, making them more challenged in a metal detection application. Then you have considerations for the packaging itself. If the packaging material itself is of a conductive nature, like a metal pie tin, a foil pie tin, something of that nature. When we look at foil films, today's sophisticated metal detectors are actually able to inspect those products and still have very good results for metal detection contamination above and beyond the package. But historically, even foil film products posed a challenge to metal detection inspection systems because, again, the conductive nature of the material itself. Metal detectors are really available in many formats and styles, depending on whether it's a bulk product or a packaged product that's being inspected on a belt. Products that are in a liquid state or a slurry state, products that can be pumped. Metal detectors are available in those applications. And there's also applications available for what I would consider free-flowing products or gravity-fed types products where the products are free-flowing through the detector itself. So many applications for this style of inspection. Basically, the way that the detector works, again, is kind of on that conductive principle where there's two characteristics of a material that makes it able to be detected in the metal detector. One is its magnetic permeability, the ability for it to become magnetized, and the other is its electrical conductivity, the ability for it to conduct electricity. Since ferrous materials have both magnetic and electrical properties to it, it typically is the easiest material to detect. Your non-ferrous materials, your aluminum, brass, lead, copper, bronze, zinc, those type materials are semi-magnetic, decent electrical conductors, so they're kind of in the middle of the road as far as ease of detection. And then the most difficult and most challenging material typically to detect on a metal detector is stainless steel because it's non-magnetic, it's not a good electrical conductor, so it's kind of the most difficult. Unfortunately, it's probably the most prevalent material within the environment that we're trying to protect against. But because of its conductive nature, can be challenging. The little animation you see there is basically a conductive material, I'll say, as opposed to a contamination, because again, it could be product that is conductive traveling through the detector, creating an output. But as a conductive material travels through the opening of the detector, basically what occurs is a voltage is created. If that voltage is enough of a voltage, a detection occurs. What's going to affect the amount of voltage and increase it to the point of detection as far as a contamination is concerned would be the type of material, ferrous versus stainless steel, or the size of the material. The bigger the piece, the bigger the voltage. Again, we need to also keep in mind that because product can also have an effect on the detector, we need to basically set sensitivities to successfully inspect the product without false rejects, and then look for metal above and beyond that. So that's kind of what we're showing there in that little animation. We talk about X-ray systems, we're going to talk about a little bit of a different principle. X-ray inspection systems work off of density principles, where we're creating an image through the use of an X-ray, very similar that if I were to go to a doctor's office thinking I had a broken arm, he's going to take an X-ray of my arm and then evaluate the image that is created to determine whether or not there's a break in my bone. Well, the same thing is happening within the X-ray inspection system. The product passes through the X-ray, an image is created, and then we're going to analyze that image. But it's working and looking for variations in density to identify foreign material. Because we're looking for variations in density, the material, the packaging material, or the state of the product as far as its conductive state have no effect on the Xray system. It doesn't matter if it's a high moisture product or a high temperature product. It doesn't matter if the material that it's packaged in is a foil film or a heavy foil pie tray. The X-rays are going to ignore those aspects of the product and look through the packaging and look for foreign material in that way. So a little bit more of an increase as far as potential applications and potential inspections maybe for an X-ray system, then there may be some limitations for metal detection. But there's also going to be some limitations for X-ray inspection solutions because although we would have inspections for packaged and bulk product traveling down a conveyor belt and for liquids and slurries and pumped product, there is not an X-ray currently available today in the marketplace for free-flowing or those gravity-fed type applications. So it's just something to keep in mind as a difference between the two types of technologies. Again, X-ray inspection is basically going to take an image and it's going to analyze that image. So here's a great example of a product that would be maybe challenging for a metal detector because it's a heavy foil bag, but for an X-ray application, it's relatively easy for that inspection to occur. As that product travels through the X-ray beam, what is created is an image. That image is broken up into individual pixels, and each pixel will be assigned a numeric value based on the level of grayscale. You can see where no X-ray energy has affected or no X-ray energy has been blocked by the packaging. The pixels are very light and bright. Then you can start to see the very edges of the packaging where it starts to get a little bit darker of a gray tone. Then in the most dense areas of that product, you can see where we have the darkest images and the darkest pixel images. The computer is going to take this image and analyze it pixel by pixel, comparing each numeric value with the surrounding pixels and determine whether or not contaminations are present. And it will run those values through several different algorithms to detect different material types and sizes. So kind of a general idea of how the inspection occurs on an X-ray system. As far as what an X-ray can detect and really what it cannot detect, this chart kind of shows you what we're looking at as far as detectable materials and non-detectable materials. We look at X-rays and we talk about X-rays. In detectability, we talk about the material's specific gravity, which is basically a measurement for its density in layman's terms. If the material is more dense than the product portfolio, it will be identified by the detector. Here we can see some materials like hair, wood, some plastic materials. PP is polypropylene. UHMW is another type of plastic. Of course, nylon is a common material that we may find in a production environment. For the most part, those materials are not dense enough to be detected by an X-ray inspection system. The majority of those materials, if you were to drop them into a glass of water, they would probably just sit and float on top of the water. However, you get down into some of these other materials like PVC, glass, stone, and then your different metal types, those materials would sink rapidly in a glass of water. That's not a 100% test to determine what's detectable or not, but it's a fair assessment as to determine what might be detectable in an X-ray system. If it floats, it's going to be very challenging, if at all possible. If it sinks, we at least have a fair chance of being able to detect that. So some of those plastic materials that we've identified, polypropylene, UHMW, in their natural form, if they can be natural as a composed material, but in their natural form are not detectable by an X-ray system. You come down into some materials that have a higher density, like PVC, polyvinyl chloride. In all actuality, it's actually the chloride material within PVC that makes it more visible to the X-ray spectrum. So what plastic manufacturers are doing is they're adding additives to plastic materials to make them more visible in both metal detection and X-ray inspection type systems. So this just gives you a high level overview of what sort of materials are detectable within an X-ray and what may be more challenging to detect in an X-ray. Of course, this also highlights why it's not only those other controls like sieving and filtering products, and magnets and things of that nature as far as a holistic protection for contamination. This identifies things that are challenging to detect, like wood and insects. So that's why we have insect and pest control programs to prevent insect infestation. We're no longer allowing wood, or really should be able to control any wood that might be within the production environment to make sure that it's not splintering or causing contamination risks. Human hair, we all have to wear hair nets when we walk into the production environment. These are things that are challenging to identify in any shape or form as a contamination, so therefore we put preventive measures in place to prevent them from happening in the first place through our good manufacturing practices. We look at some of the factors that can affect sensitivity. I'll first kind of look at metal detectors. Number one, the physical size of the detector itself is going to impact detection capability. The bigger the detector is, the less sensitive it's going to be. There are also location differences for sensitivities within that opening space, the center of the opening being the weakest area for inspection, and as I approach any of the edges of the detector, those are the most sensitive areas within the inspection area. We also have to take consideration in for what we would call orientation effect. We typically test and challenge and validate and verify inspection systems with spherical contamination, little small BB test samples of metal. Well, in reality, your real world contamination is not going to be a perfect BB. It's going to be more irregular shaped, maybe even a piece of wire, maybe even a piece of the screening material that we use to try to protect ourselves against contamination in the first place that breaks loose and it causes contamination. That's going to be a piece of wire. That's going to exhibit some sort of orientation effect as it travels through the detector. In one direction, it will be easy. In another direction, it's going to be more challenging to identify. So that's important to understand, not only when we're trying to validate the detector's capability, but also when we're looking at these detectable materials that people are now providing that are now metal detectable and X-ray detectable type plastics. We need to understand that if it's a whole piece of the pen that breaks off, or if the pen shatters and a splinter of the pen breaks off, is it going to exhibit an orientation effect as it travels through the detector? These are going to be some of the things that we want to look at when we're determining the detectability of detectable products. X-ray inspection. We have some considerations to look at the when a product is very homogeneous in its density, like say a block of cheese, inspection is relatively easy to determine as far as location of contamination in relationship to the product. Doesn't matter if it's embedded in the product, if it's sitting on top of the product, if it's underneath the product. Inspection capabilities are pretty much going to be even throughout those areas because the product itself is homogeneous and has even densities throughout the product itself. But if that product were a shredded block of cheese, now there's variations inherent in the product itself's density and therefore may have variations in detection capabilities at those various locations of density. Here we can see there's some peaks in the product portfolio and there's some valleys in the product portfolio. Well, if the contamination sits in a peak area, detection is easy. But if that contamination is sitting in a less dense valley area of that product, it may be more challenging. So again, I'm just pointing out some of these considerations, not only for determining what the capability is going to be for your metal contamination spec, or in case of an X-ray, a glass spec or a stone spec, but when we're looking at, are these available detectable plastic materials? To what level am I going to be able to achieve detectability of those? We need to take these things into consideration. Orientation effect with metal detection, variations in density within the X-ray inspection system. So here we kind of see some of the development of detectable plastics. We've seen a lot of product recalls in the last few years for blue plastic lining material. So we've got a bin full of product. There's a bin liner in there. When they process that or pour that bin in through the further processing, a piece of that bin liner tears off and ends up as a contamination. I've seen product recalls of several tens of thousands of pounds of meat product due to blue plastic lining over the course of the last few years. So what manufacturers are doing, and I work very closely with an organization called Detectability. In fact, that's where I got most of this image from, so shout out to them. Very good group of people. There are many manufacturers out there now that are making detectable materials, but as far as a very holistic portfolio of available items, I don't think there's any that come as close as what Detectability has to offer the industry. What they've done is they've formulated various materials and added certain minerals into that polymer to make it more visible to metal detection in X-ray systems. We're all probably very familiar with metal detectable pens. That I think was probably one of the first items that became available as a historically a difficult and challenging material to detect that was now modified to make it more detectable in the marketplace. There's now many items from personal protection gear, hair nets, beard nets, scrapes, buckets, scoops, brooms, gloves, anything you could think of is they at least have it made to some level of detectability. Whereas, again, historically, if a piece of the pen or the scraper ended up in the finished product, the consumer was the first to find them, and that typically would result in that expensive recall and brand damage. Now that those products are available, I'm starting to see a lot more of them utilized in industry. In fact, when I go and audit a facility today, that's one of the questions I have to ask is, do you have metal detectable pens available so we can take notes out there? And if they don't, well, then I'm going to take the ones that I've been supplied to for me, because it is important to understand. I was doing a little bit of studying because, of course, metal detectable and X-ray detectable polymers is not necessarily my area of expertise, so I wanted to do a little bit of studying on my own. And there's an abundance of material available. It's important to validate the detectability of the materials that we've chosen. I did find a study highlighted that some of the results from testing detectable materials kind of raised some red flags for me. So this was the chart that was provided. And from what I could understand from the study, they took a 1.5 millimeter sphere of metal, ferrous, which would be a very common normal test sample used in metal detection standards, very, very common size. And then they took various detectable materials from different suppliers to determine what the equivalent size would need to be of the material in order to give the same amount of signal as that 1.5 millimeter piece of ferrous. And you can see here that it's quite astonishing. In most cases, even upwards of 20 millimeters square, those materials barely gave the same amount of signal as the 1.5 millimeter size contamination piece. So we need to understand not only, and you can see there is also some variability between suppliers as well. So certainly these organizations claiming that these materials are detectable is certainly true. They are detectable. But we need to truly understand what that detectability is and validate those to prove out not only the detectability of the material, but also have to have a good understanding of if a problem goes wrong, to what level are we truly being protected from, and then determine whether that investment is worth it. I'm hoping you'll find it is, because I do believe that there is value in having some of these materials within the production environment. I'm just letting you know it's important to understand the true capabilities and what may be specific for your particular product, application, or product type. Because the impact of sensitivity is very impactful. This chart kind of shows a detectability of, say, 1.2 millimeter and the impact that that has in what we would call more realistic real-world contamination, where we're exhibiting some sort of orientation effect, and these are all in their worst orientation. So I really call this my scary slide, because this tends to scare some people. Everybody thinks that, hey, I'm detecting 2 millimeter just fine. I'm not detecting 1.8, I'm not detecting 1.5, and I'm certainly not detecting 1.2, but in my case, 2 millimeter, that's fine for my spec. Well, you can see what contamination wire sizes are actually able to get through the process. Certainly, any of those ending up in a food material and discovered by a consumer would at the very least end up probably in a customer complaint, if not a further investigation requiring a full-on product recall. So sensitivity is important. It's important to get down to the most sensitive setting that you can, but you still need to be able to successfully run good product. And that's really where we do things like validating the system, where we're going to determine what level of detection ability we have and prove it out. Validation is a requirement in many and most food safety program standards and regulations. So it should be something that you're familiar with. But I think where industry tends to struggle a little bit with validation is regulators say that we have to validate systems, but they don't really give us any good guidance as to what they consider good validation. So the difficulty is in determining the number of samples that we're going to run. In some statistics sampling, the confidence level could have you run up to 10,000 samples if you wanted a 99% confidence level. But is that enough? Or is that too much? Some facilities I see do a validation study of maybe 10 passes of product, but statistically, what sort of confidence level is that providing? It's probably on the lower end. So that's one thing we need to determine is what is the confidence level we're trying to achieve, and then statistically, how many samples do we have to run and get a 100 out of 100 marking in order to be within spec of that confidence level. I'll tell you what I've found most industry settling on is about a 30-pass test, where they're running 30 passes of product to make sure that they don't have any false rejects occur, and that will help them set their false reject rate, their FRR. They're then taking, at those same sensitivity levels, various sizes and types of materials, passing them through the most difficult location of the device, and determining what the detection level capability is by looking at their, once they find the sample that gives them that 30 out of 30 detection capability, that gives them their probability of detection information. And so that information can be used as your validation study. Of course, it should be documented. You should take into consideration what's going to work for your individual facility. If you only have one product to validate, maybe 10,000 samples is doable. But if you have 10,000 products to validate, maybe 30 is what you want to settle on. You'll need to consider basically where in the process the control device is located, what sort of system type it is, may also have an effect on whether or not we're able to access the weakest area. Here's some examples of, again, a pipeline application where the center of the detector is the least sensitive area, but in this particular case, the center is not accessible because that's where the product pipe is. Now, certainly you could inject the samples directly into the product flow itself, but then you need to ensure that you have a measure to retrieve those samples if the detector doesn't detect them. So we don't want them going on into further processing. You also have to take into considerations when we're putting stuff directly in flow in direct contact with product, that either that product should be disposed of, or we need to understand any cross-contamination risks or sanitation risks of the samples that we're using. We need to take those things into consideration when we're actually injecting the product and having direct product contact. We also need to look at, when we're validating these things, not only the detection capabilities, but also the operational capabilities. What I mean by operational capabilities is the operation of the device when we get a detect event. So we get a detect event, did the reject device remove that product from the line? If there's 4 packages of contaminated products in a row, is the reject air pressure sufficient to remove all 4 rejected packages? So those are some of the things you want to consider when we're going through that validation. So I think I'm coming up with about maybe 15, 20 more minutes worth of time. We wanted to give some time for some Q&A. Certainly you see here that Mettler Toledo's information with our website located there. You can go there, find all sorts of information and white paper regarding some of the topics that we've talked about. Our technology guides are some of the best information guides you could have on the various technologies, on how they actually work and how to properly implement them. I encourage you to go to the Detectamet website. Again, a shout out to them and thanks for their images that they supplied for me, to see what sort of materials are detectable out there. And I challenge you to understand their true level of detectability. Detectamet has done a very good job of going through and ensuring, as they formulate these items, that the materials themselves do not become more fragile and pose an increased risk for contamination. I mean, that's the last thing you want to do is purchase a metal detectable, a broom with metal detectable bristles on it and have it be weaker than a standard broom and have all those bristles fall off as contamination, whether they're detectable or not. So be sure that you're partnering with a good, reputable company like a Detectamet when you're looking for those detectable materials. Mettler Toledo is certainly happy to assist you in some of those inspections and challenges that if you wanted to send us some product along with some of the detectable materials in the sizes that you're willing to investigate, we'd be happy to run them through some systems and provide some reporting back to you. So yeah, I guess with that, let me open it up with any questions that there might be.
Okay, thanks very much, Robert. Can you switch your webcam on and stop sharing, and then we'll take questions. You can hear me, I take it. Can you hear me, Robert? Yeah.
Yep.
Okay. Great, thanks very much for that, Robert. Oh, your webcam's gone off again.
Sorry, I took a drink.
All right, okay. No, that's really good.
It's just juice. It's not beer. So.
Yeah, excellent technical information there, Robert, as usual. And I'm sure the ladies and gents at the registrants, when they get the webinar and also the slides, a great reference. So, okay, throw it open to questions. So I've got one here from Rishika, can different product formats and sizes be passed through the same metal detector or X-ray?
Yeah, so I mean, obviously, with the metal detector, there's some more physical characteristics that are limitations. Obviously, if it's I can't fit a product through the detector if it's bigger than the detector opening itself. But as far as different product types or conditions, as long as they can physically fit through the aperture, yes, they can be inspected through the same thing. But there may be differences in the detectability for the different products and different sizes. Again, if there's any kind of conductive nature for the product, the more signal. So if I have a large amount of product versus a small amount of that same product, the small amount is going to be able to run at a higher detection capability. As far as X-ray is concerned, we're typically limited by the beam geometry. So when we do have an X-ray, basically you have a source, and then the beam geometry comes down in kind of a conical shape. And so the portfolio of the product needs to fit within that conical shape of the beam geometry in order for all areas to be inspected. So there are some limitations there again, depending on size, but typically we take those into consideration. What is the smallest product you're going to run? What's the biggest product you're going to run? And then we want to be able to supply the appropriate device in that case.
Okay, thank you. Isabella, metal detection, what test piece sizes are you using, and do you see false rejects with this?
Yeah, so that's the kicker, right? I mean, everybody's wondering what spec size is too small, what spec size is too big. How do you deal with setting it up for the product or false rejects and things like that? So my answer to that question is that if it were my facility and I were running the plant, how I would want to know is I would set the systems up to successfully run production. If there's variations in production that I'm going to accept still as good quality product, I want the device to accept those variations so that when they do occur, I don't get a false detect. So I always say you set systems up to successfully run product and all variations of product that are acceptable, and then you challenge the system to understand what its true capabilities are. Once I found that sensitivity setting that runs all the conditions of the product with minimal to hopefully zero false rejects, then I'm going to place those test samples in the most least sensitive area of the device and see what it's able to detect and say that that is what my achievable spec is. When you start to set the system to see a spec and it adversely affects how it's running production and increases your false detect rate, that's the balance you have to come to. They're not intelligent devices. We set them to inspect a certain product condition. If that product condition varies, they don't know any reason why. They're just affected by it. So when you talk about what size piece, depends on the inspection, depends on how it's set up, depends on the application if it's been spec'd properly. It's a challenge, right? Because I have yet to walk into a production environment where I have a single product running on its own individual production line. Most of the times we have multiple products running on an individual production line, and therefore the size of the detector has to be big enough for the biggest product. It's going to affect the overall performance of some of the other products. So it's kind of, we get into a state of, well, we just have to live with it. It's as good as it's going to be. Well, it's important to understand what that limit is so that you can really make an informed decision onto, well, is that good enough? And if it's not, how can I put other protections in place or improve my process to ensure that these things don't get through? Because it's important, not only from a consumer perspective and protecting the consumer and from physical harm and potentially death from choking hazards and things like that, but also from a business standpoint. I mean, obviously those sort of incidences affect negatively the business and is very impactful from a business sense. So it's that balance.
Okay. Latha, can you please explain if there is an acceptable range for number of acceptable false rejects? For example, if you see 5 rejected packages and you run them through the metal detector again and the machine passes all those 5 packages, can you consider 5 as an acceptable false reject?
So, I mean, from a business perspective, false rejects to me are money. So I don't want any false rejects. That's either time and money to rework that product, as you've mentioned, or it's time and money because I don't trust the rework process and I'm just going to go ahead, and I trust the detector, I'm just going to go ahead and dispose of those products. So when we look at specking systems and partnering with organizations, oftentimes we see a qualification in their desired achievable false reject rate is less than 1 in 10,000. That's probably a very common goal. Now, there's very few systems that are set up the way I would set them up to successfully run production and be within that 1 in 10,000 false reject rate. But if you're having, 5 false rejects in a row, that's probably outside of the scope and far superseding that acceptable rate. I don't like to rework rejected product through the exact same system that they were inspected during production. The reason being is things like orientation effect. If I have a loose contamination in that package and it shifts its contamination position, it may not be detectable on that second rerun pass. So now when you look at that statistically, the first time it was detected, I ran it one more time and it wasn't detected. Well, the first time I don't have confidence in the metal detector because it detected something. And I don't believe it. It must be broke. So let me reinspect this package. And when it doesn't detect something the next time, now you have confidence in the detector and everything's working great because it didn't detect something. And to me, that doesn't make sense. It should be the opposite. And if you look at that statistically, I've got a 50% chance that package is contaminated. I only ran it twice, and one time it said it was contaminated, one time it said it wasn't. When you talk about things like position sensitivity differences within the detector, like orientation capabilities and effects on the detector, that statistic probably getting a little bit higher on the contaminated side than it is on the not contaminated side. So if you're going to rework a package, ideally it's done on an offline system that's much more sensitive than your online system. Or if it's done on the same system, we're reinspecting that package multiple times through the device, trying to reorient the package, turning it upside down, causing chaos in the package. And if the first time it was contaminated and it detected something, and then I ran it 5 more times and it didn't detect something, now I can maybe look towards that was a false reject. But then you want to figure out, well, why was it a false reject? Is the detector not set up correctly? Was there a condition of that product that changed drastically outside of the normal, and that's why it occurred? Those are reasonings you want to have so that you can prevent those from happening in the future. The worst thing you want to do is not have confidence in your inspection device and spend all of your time reworking product that shouldn't have been rejected the first time it was produced.
Makes sense, yeah. Okay, David, I work with a completely dry production facility. This seems to apply more to wet production facilities. Where on my line would I apply the metal detection method?
Yeah, so the dry product facilities are typically for a metal detector an easier application because the product doesn't have an effect on the detector. It's dry, it's non-conductive. So the detectors are able to run at their maximum sensitivity settings because the product itself doesn't have an effect on it. So therefore you're able to get the best out of the detector. So really the only limiting factors at that point are going to be the size of the detector. And that's where it's going to come into an application standpoint. So if we're running bulk product prior to packaging, a gravity-fed detector we can have. The product just simply free flows through the metal detector. It's got a reject diverter. When it detects something, and it diverts the flow to a different location, to a reject bin. That's going to depend on flow rates as far as what size detector we need. Obviously, the smaller detector is going to have a limit on the amount of product that can flow through there per hour. A larger detector, we can get more product through there an hour. If it's in a packaged position within the facility, then it depends on the package type. Typically, we're going to inspect products that are filled into very large super sack bags, 5,000 pound bags of product. we're going to inspect that through a gravity-fed system with a diverter system. So the good product goes into the 5,000-pound bag, and the diverted product goes into a reject bin, because I don't have a system where I can run a 5,000-pound bag through it. But if I have a 50-pound bag of product that's been a package, certainly I can inspect that through a conveyorized type detector. Smaller pouches, I can go into even smaller detectors. So many applications, and it's very common in those dry applications. And quite frankly, those are the ones that I prefer to be in. The worst case is that they can sometimes be sticky if it's like a sugar factory, but it's certainly not gross and stinky like a meat producing facility. Those can be a little bit unappetizing, but I love them too. They're some of my favorite customers. I don't want to, say anything bad about them.
Let's move on. Isabella, are you able to detect broken glass in glass packaging?
Yeah, so that's certainly one of the biggest inspection challenges that there can be for any device is really glass, because one, it's not conductive, so obviously metal detection is kind of out of the story. Sometimes the vision systems can do very well, but challenge with vision systems is oftentimes the glass material that we're looking to identify as a contamination is a piece of the actual packaging material. So visually, they look the same. Same challenge in X-ray. We're looking at density of the object. So the density of the packaging material itself is the same material of contamination density that we're trying to achieve and detect. So where we have an increase in capability to detect glass-in-glass applications for X-ray is when we have X-ray inspection devices that have multiple X-ray either sources and or detectors, but really what I'm trying to say is where we're visually looking at the product instead of just at one perspective. We have multiple perspectives that we're visually inspecting that product on. Because what happens in an X-ray system is we have to take the glass packaging and put a slight masking tool around the package itself to ignore it. Then we're looking for contamination in the other areas. Well, if I only have one vision of perspective, if the glass is behind a masked area of the package, it's hidden in the mask. So when I expose it to different angles, now I can see where that contamination is based on that particular angle as it travels through the inspection system. So multiple beam inspection systems. In fact, we have a system that's specifically designed for glass-in-glass inspection systems. Very controlled in the product handling is important also, so that we have spacing. We don't get glass bottles or jars that are back to back and butt to butt, so we get a gap between them. So there's a lot of nuances and intricacies that are designed in those applications where it's not just simply plopping a system in line and going for it. But possible and very common.
Pretty impressive. Okay. Tim, what success have you experienced with X-ray detectable band-aids? We seem to be having trouble detecting them consistently.
Really, again, any detectable material depends on what it is and how they make it detectable. I can give you an idea. I know, I'm not really sure exactly what they're doing now, especially with the X-ray detectable bandages, but metal detectable bandages had a little small aluminum strip underneath of the pad, if you will, on the Band-Aid. Well, that's okay if the whole Band-Aid fell off. But if just the sticky part of the Band-Aid tore off of my finger, that's still a contamination, but there's no detection capability on that little sticky part of the Band-Aid. It had to be that aluminum strip that was in there in order for it to be detected. So that's where I'm saying, certainly there are manufacturers out there that develop and have developed really good detectable materials. But as you look into investing in those sort of materials, you want to go through some investigation, understand what its true detection capability is going to be. There may be that this, again, not knowing this particular situation, what the product is, what the system type is, and all that sort of stuff. It's hard for me to give them a pinpointed answer, but that it's exactly what you need to do is you need to go through trials and tests to determine okay, is this particular Band-Aid or style of material detectable in my particular application? Because it's going to be different. Each application, each product type, and really even the same product type in a different facility could be manufactured in a different position within the process. So, it's hard to say.
Okay. Michelle, we are an organic facility. X-ray machines. Our certifier tells us some are okay to use and some are not. Irradiation is their concern. Are there types of X-rays to look for to avoid their concern?
So when we look at Xray Systems for inspection, so for foreign material inspection or for product quality inspections, where we're visually analyzing that X-ray image, those sort of systems are considered and classified as what they call cabinet X-ray systems. It's very similar to the X-ray system that we all go through, our baggage goes through at the airport. That's considered a cabinet X-ray system. There are regulations around the amount of energy and how much emissions can be exposed from that. Those cabinet X-ray systems, based on all the regulations, even globally, that we deal with, there has been some studies out there that basically state the levels of X-ray is so low that there is no effect on the product's condition, quality, taste, smell, molecular structure. There's no effect in that way. And so those cabinet X-ray systems are classified and available to be used in organic processes because they have zero effect on the product itself. Now, when you look at X-rays used for irradiation, where we're using it as a control method for biological and microbiological type contamination concerns, that's a totally different story. Those systems are tens, if not hundreds of times more powerful than a cabinet X-ray system. Those obviously do have an output effect on the product itself because its intention is to do just that, is to irradiate the product to make it more, I guess, sanitary or, from a biological sense, safe in that fashion. So two totally different types of systems. One, yes, can be classified and used in organic. The other, the irradiation, I do believe that there are some that claims, and again, I'm not an organic expert, these made and they're changing all the time. I do believe that there, at least at some point, has been some restrictions of use of irradiation of organic products and maintaining that organic certification.
Okay. Pauline, we observe that detectable plastic materials are usually more breakable than non-detectable plastic. Therefore, since they are not so well detected, isn't the risk of foreign body really increased?
Yeah, and that's why, in kind of coming up with this presentation and going through and learning some myself, going out there and trying to find some information, I agree. There has been some studies that show, and they do like the tensile strength. So they'll take the metal detectable broom and they'll pull it and see how much it takes to pull it apart and actually break it apart. And then they'll take the regular broom bristle and do the same. And the studies have shown that, yes, in some instances, some of those materials do become more fragile, more elastic, can be more shattered when they break as opposed to breaking off smooth edges. So there are some potential risks in going down there. And that's, why I wanted to be sure that I pointed out some of those things as we talked about it. The other thing that I learned in kind of looking at some of these things is you also need to look at it from a surface perspective. So whether it's a plastic material that you're using that's metal or X-ray detectable, or that broom bristle or whatever, the surface of the broom of the metal detectable materials, when you look at it under a microscope, it's not as smooth as the other one. So now I'm taking this broom to clean a product area. Now I need to clean the broom to make sure that I'm not doing any kind of cross-contamination. Well, with a metal detectable broom, because of the surface area of the bristle, it's more difficult to clean and sanitize than it is the standard broom. So those are all things that certainly, yes, I am not going to sit here and I'm a metal detector and X-ray expert. I'm not a detectable plastics or broom guy. But those are some of the things that I discovered as I was trying to understand a little bit more of that I would certainly encourage anybody to look into if they're looking at going down these materials. I agree. Some of the studies have proved that in certain cases from certain manufacturers, I wouldn't want to claim any of them, that there were tests that showed that some of those detectable materials became more fragile and, you're correct, at that point increased the risk of it becoming a contamination. That one slide I showed you, a 1.5 millimeter piece of ferrous metal, the detectable size of the plastic was nearly 20 millimeters. So again, you need to understand the detectability, what effect it's going to have on the tensile strength of the material, if you will, and whether that's going to increase or decrease the risk, and whether it's something that's worth the investment, because it will be an investment.
Okay. Joran, in case of X-ray detection, are systems through algorithms able to distinguish between overlap of multiple products, higher density, and actual contaminants?
Yes. Basically, some of the different algorithms that we run it through, it's looking at, just as an example, if I had a small tool algorithm, it may only compare 2 pixels when it's doing the numerical pixels, and it may do that comparison only in 2 different axes. So it's looking for a very small difference in a small area. But if I had a large contamination and I'm only running it through that small algorithm, well, now the density variation comparison is happening in the contamination itself, which doesn't see any difference in numerical value, so it doesn't see it as a contamination. So that's why we would have a large tool that's going to compare more pixels in a larger direction and on more axes as it's looking around that item to do some differences. There are some systems out there that have varying levels of power, and that's really where you can start to see some increase or decrease in contrast of materials as well. So rather than having a system that is stagnant running data through a single algorithm, inspection systems today are very smart. They're variable power. There's multiple algorithms that we run the data through in order to determine that. So there are also the manner in which and the order in which we analyze the data. An example, some products have an oxygen sensor, what they call a desiccant package inside of them to keep the moisture down. Well, that obviously is a surface area that is different than the product area when we're inspecting it through an X-ray system. So 2 things have to occur in that inspection. Number 1, the customer wants to ensure that the package is actually in there, because if it's not, then it's going to get moisture and spoilage is going to occur sooner. So they want to confirm that that little oxygen scavenger is in there. But then they want to be sure that they can investigate for contamination, not only at that scavenger, but if the contamination were underneath of that scavenger. So in that algorithm, we'll do a object finder, find the object first, and now that we found the object, okay, now ignore it, and then do the sensitivities for the other algorithms to look for contamination. So yeah, today's systems are very intelligent. They're getting more and more intelligent every day. New capabilities are out all the time. So it's probably one of the more rapidly advancing areas is within the inspection for X-ray inspection than any other inspection.
Okay, Robert, they're not running out of questions. I wonder if you could do sort of one-word answers. Is it possible to, Krista, we produce starch and often see false rejects on our line metal detector due to static of the product. Is there a way to adjust the detector to avoid?
Not so much on the detector itself. The only thing you can do to the detector itself is really turn down and decrease the sensitivity, which obviously is going to have an effect on what it can detect at that point. So in those applications, a lot of times what we use is the throughput tube that is going through the detector. We use a material that they call, I believe it's called Tyvar. It's an anti-static material. So that tube is impregnated with a material that is conductive. We then wrap a ground strap around that tube to dissipate the static to a ground point, as opposed to allowing that static discharge to occur through the electronics of the system. That's one way to do it. There's also ionizers. So we basically have an air ionizer. So the air around the device, you ionize it so that it doesn't allow the charges to line up correct to create static. So there's a few things that can be done. It just depends on the age of the system, the materials that are used in there. But the only thing on the detector side that you can do to it that it's going to have an effect would be to turn down the sensitivities. Typically, those sort of incidents, whether it's a static, whether it's an electronic interference from some other device, we always try to solve them at the source as opposed to trying to affect the detector's performance in order to resolve the issue.
Okay. Just a couple more then, because we are over time. Riyadh, does the humidity of the environment affect the metal detector?
Not so much, other than it can affect things like static. So typically, we don't have static issues here in Florida very often, but certainly I've got manufacturing facilities up in the Northeast, the New York area, or wherever, that during this time of year, when things start to cool down, humidity's less in their plant environment. Now they start to get some static issues from the plastic belts just rubbing on plastic decking and the plastic bagging material. So yes, those sort of things are there that can affect the static, ability to create static, and humidity can be a factor. It's why we typically see these static issues arise and these questions start to spur up a little bit more this time of year around static.
Right. Okay. Andre, is it needed for the supplier of metal detectors to validate the test pieces every year that is given by themselves? So do we have to validate the test pieces every year?
Not necessarily. So we do offer and supply certified test samples. I believe they come with some sort of certificate of authenticity that shows what the material type is, what the size of the material is, and I believe that has a certificate that I think is maybe a 5-year certificate that's available on that. But as far as validated, you can buy certified system. What I often tell people is if you're going to have 100 different sets of test samples in your facility, maybe have 1 or 2 that are certified. The rest you don't need to have certified. The certified ones you want to use for activities like validation, maybe a higher level quality check than your normal just everyday routine verification activities. Don't, because there will be an increased cost. So from a value perspective, most regulators want you to have some sort of traceable certified sample set that can be used for activities such as validation or when the auditor is there. But through daily activities, I haven't seen one regulation that actually specifically states they must be certified test samples used for these activities. So it's often up for the discretion of the auditor.
Okay. Pauline, some foreign bodies are visible on the X-ray screen but are not detected by the machine. Are there systems which would allow us to detect unusual forms?
Yeah, so that's where some of the advancements in X-ray inspection and how we're designing the X-ray generators themselves and the detector arrays themselves to do things like what's kind of being spoke about here. Yes, oftentimes you will see the visual anomaly by looking at the screen, but the X-ray system may not have tagged on any of the algorithms that it sent the data through. It just wasn't enough of a difference to have that occur without increasing sensitivities to the point of having other features within the product start to create false detects. Again, it's that balance that you have to come through with sensitivity and successfully running production. That's often why you'll see There are some companies out there, in fact, we even offer a service for X-ray reinspection, where you have a set product that you believe may have contamination in them, and you want to run that product through the device to determine whether or not it's contaminated, and if not, release that product into the marketplace. Maybe that product's been put on product hold. There's a couple companies out there that do it. Mettler Toledo, I believe, offers a service similar to that. But what they're doing in those cases is it's not high-speed production environments. I'm not running 10,000 packages a minute. I'm running 10 packages a minute, to where then I am visually analyzing the image myself, not allowing the electronics to come up with the determination whether a contamination is there or not. That's why often you'll see much better specifications in those applications from a rework perspective than you would see during normal production capabilities of a standard inline inspection device. Because at that point, we aren't allowing or relying on the electronics to do the inspection. We are visually making the decision ourselves as to whether we believe that is a conforming product or not. A lot of regulation and specifications around then, as far as now I have to give myself a break every 15 minutes because staring at the screen all the time is kind of mundane and boring, and I might miss something if I don't. So there's a lot of requirements when you do things like that, but that is not necessarily an uncommon thing. That just happens to be that the density of that particular item isn't enough for the algorithms to pick up on it electronically.
Okay. Robert, could recycled packaging material of carton cause false rejects?
Yeah, for sure. Certainly in metal detection application, we see it more often than we do, say, in X-ray application, because in X-ray application, often when we're doing cardboard boxes, we're putting some sort of masking tool in place to ignore the cardboard area. But yes, recycled cardboard material is synonymous with having bits of metal embedded in them and can certainly be a nuance. I'm all for saving the environment and utilizing our resources and sustainability and all those things. But recycled cardboard is a nightmare for a metal detector man because it is oftentimes a source of false rejects. The only example or the only suggestion there would be, if possible, and oftentimes it's not, but if possible, if we believe that the contamination is due to the packaging material, if we can remove the product itself out of the box and just run the empty box, let the empty box set the detector off and prove it out. I often will take that empty box and then rip it in half and send the halves through, figure out which half is contaminated, rip that in half, and just keep breaking it down and breaking it down and breaking it down and breaking it down, and then documenting how much time it took me to do that. I'm going to keep that little piece of metal, what batch and order it came in from my cardboard supplier, and then after I build a case after about 3 months, I can take the list to them and say, hey, look, you need to do a better job. How about you install a metal detector before you send me this stuff?
Yeah. Okay. Rishika, can you change the sensitivity of an X-ray machine just like you can in a metal detector?
Yes, there is adjustability to sensitivity. There is also what we consider different program recipes. So I can have product 1, certain sensitivity conditions, product number 2, different set of certain sensitivity criteria. So yes, certainly possible in both technologies to have the ability to adjust sensitivity and to have some sort of product list in there that is retrievable and storable.
Okay. Maria works in a herb production facility and doesn't have a metal detector. Does she need one?
Well, I think yes, everybody needs a metal detector and X-ray system. No, the reality is it's you need to conduct a hazard analysis and determine whether there's any risks for physical contamination, what those risks are and what those materials are, and then find a way to control those risks. Metal detection or X-ray inspection may be a solution to do that for you, but it may not be a necessity. I certainly don't want to put devices in place where they're not necessarily needed, and there are other means of controlling that. But it's a requirement depending on, of course, if you're exempt from certain regulations. You may be an exempt facility where you don't have to do those sort of things. But pretty much if you're a non-exempt facility or at any level of certification or regulation facility, you at the very least need to go through a basic HACCP procedure and do a hazard analysis, identify those potential risks, and find a way to control them.
Okay, last question, very technical one. Tim, talking about the crop or masking feature for the jar example, is this an actual crop of the image, or is it a function of defining and reducing the pixel range within that location?
It can be both. So for the most part, it's typically done within the software itself, where we're just doing that. We're looking for a certain gray level on a particular pixel, and then using that to create a mask to say, hey, ignore these pixel areas, as opposed to a physical mask that's being done by hindering the X-rays from inspecting that actual area. Now, that being said, there are some applications where we've done that. Maybe in a bottling application where I don't want to have the metal cap affect any kind of the algorithm setting during an auto setup, so I mask out the cap itself, and it's set outside of the X-ray beam. Can either be done physically by adjusting the X-ray source itself and the angle and the position that it views that product at, or it could be done physically by putting a physical barrier in there. Can also be done electronically through the algorithms, just as we do the bottling tool. So it really depends on the application, what we're trying to achieve.
Right, on that note, it's funny, you thought the presentation was short and we wouldn't be able to fill an hour, and we've actually gone 16 and a half minutes over. Incredible. Every time though, Robert, we have lots of questions, don't we? It's great.
That's good though. I'm very happy with the interaction of the people that join these. I always say that I think you do a great group, and the IFSQN website is just a fantastic resource, and the things you do is a great value to the industry. I love the community that you've put together, and the people that join us for these. Always great questions. It's always super exciting me to see when they log on at first and seeing where they're all saying hi from, in Jamaica and Romania and all over the world and everything. And so for that, I do thank you for putting this together and having that platform for us.
Yeah, it's great all around. Thanks for your input, Robert. It's been great today. Enjoy your weekend traveling around the world, sampling food at is it the Epcot?
Yeah, going to Epcot, the Food and Wine Festival this weekend. So I'm going to be enjoying all the world's cuisine and drinks an hour from my house.
Have a great time. You deserve it. Take care, mate. See you again.
Thanks.
Soon.
Appreciate it. Thanks. Bye.
Okay, ladies and gents, I've already loaded the certificate in the sidebar, so you can click on download now, and you can either print and sign it yourself or open it in Microsoft Paint and type your name. Okay, yeah, we've got another webinar next Friday, and that is with George Howler of Safe Food 360, and that's measuring, monitoring, and oversight for food safety compliance, how to build a compliance model for your food safety management. So hope to see you again next week. Thanks for your attendance today. Thanks for your input. Enjoy the rest of your day, wherever you are in the world. Have a great Friday and enjoy your weekend, and we'll see you soon. Take care. Bye.